Welcome to the deep dive. For years, the story in AI was, well, it's pretty simple. Scale, scale, and then scale some more.
Just make the models bigger.
Exactly. The whole last half-decade was about this brute force scaling idea. More parameters, more data, and just hope for the best.
But the 39th annual NeurIPS conference in 2025, that felt like a real turning point, the end of that kind of unchecked optimism.
Yeah, this was more than just another conference. It felt like a watershed moment. We saw these three big shifts all converge. Architectural introspection, what's being called agentic systematization, and a real move towards scientific integration. So our mission for this deep dive is to pull out the 5 core themes that define this transition. We're going to show you how the era of discovery is finally giving way to the much more demanding era of, well, refinement and deployment.
And that shift it's absolutely necessary. The research all pointed to this one tough reality. We've hit severe diminishing returns on pure scaling.
So doubling the compute doesn't get you double the capability anymore.
Not even close. So the whole movement has pivoted from, quantity to quality. It's about surgically solving the fundamental inefficiencies that have plagued these models from the start.
So we're talking about attention mechanisms, resource limits,
Reinforcement learning roadblocks, all of it. Okay, so let's unpack this and dive into what that transition actually looks like on the ground.
Right, and we have to start with the physical setup of the conference because it felt like a direct, manifestation of the global state of AI.
You mean the two cities?
The two cities. NeurIPS 2025 was held in this unprecedented dual city format, San Diego and Mexico City. And this wasn't a choice, it was a necessity.
It was a striking situation and frankly unavoidable. The whole logistical headache was driven by this increasing geopolitical friction, and the U.S. visa regimes are just getting more and more restrictive for researchers.
So the conference itself physically split the AI world in two.
It really did. The Mexico City venue wasn't just some overflow location. It was a necessary hub. It was an acknowledgement that so much crucial research is happening outside the traditional Western centers.
And you could see that perfectly in the institutional rankings. People were calling it a violent upheaval.
Yeah, that's a good way to put it.
For the first time, Tsinghua University has basically closed the paper acceptance gap with Google. It's 4.73% for Tsinghua, 4.84% for Google. It's razor thin.
And that number, that tiny gap, it signifies a huge qualitative leap. We are just past the point where the major architectural breakthroughs are guaranteed to come out of Silicon Valley.
So a breakthrough is just as likely to come from Beijing now as it is from Mountain View.
Equally as likely, we've shifted from a very U.S.-centric model to this robust multipolar research ecosystem, which is fantastic, but it immediately leads to the next crisis we saw at the conference.
That's the perfect transition, because if the number of high-quality papers is exploding globally, what does that do to quality control?
It breaks it.
The peer review crisis hit its absolute apex, over 21,000 submissions. And this is where it gets really interesting, with the rise of the AI feedback loop.
Exactly. You have papers that were heavily AI-assisted being reviewed by what looks a lot like AI-generated reviews. And it creates chaos.
So you get these reviews that are super generic.
Super generic, critiques that hallucinate baselines that don't even exist, really shallow engagement with complex work. It's becoming almost impossible to tell when a human reviewer just offloaded the work to an LLM.
So what does this actually mean for you, the listener? Well, this crisis forces a really rapid shift in what we value as scientific merit.
Right. If an AI can fake novelty just well enough to get past the screeners, the whole field needs a higher standard.
So we're seeing this massive new value placed on empirical rigor things like reproducible benchmarks and on theoretical proofs.
Because those are much, much harder for an AI to fake or to hallucinate. This whole crisis is kind of pushing AI research back towards hard fundamental science, back to mathematics and systems.
Okay, so if the problem is diminishing returns, the solution has to be architectural efficiency. For almost a decade, we just accepted that the standard transformer had this quadratic complexity, ON2.
Yeah, that was just the painful cost of doing business.
And that ON2 barrier, that's what made processing really long context basically impossible.
And just to put that cost in perspective for you, if you double your input length, the compute you need quadruples. It just explodes.
Which is why the smarter is better dogma finally broke through this year, and it won the Best Paper Award.
Absolutely. The best paper from the Alibaba Quinn team was on gated attention. It was this fundamental challenge to that quadratic bottleneck.
And previous attempts to fix this, to linearize attention,
Yeah.
they mostly failed, right?
Yeah, they did because they stripped out the model's ability to do precise recall, which is kind of the Transformer's superpower. But their solution, it's just so elegant. They introduced a gated linear attention mechanism.
Okay, so what does that mean?
It means they stick a data-dependent sigmoid gate after the linear attention part. It seems like a tiny footnote, but it had this huge triple effect.
And this is the aha moment for you, for understanding the future of efficient models. So first, the gate reintroduces the nonlinearity that you need for complex feature selection.
Right. Second, it naturally induces sparsity. It learns to just ignore irrelevant parts of the sequence, so it focuses attention only where it matters.
And the third effect is the real game changer.
It is. It makes the model attention sink free. See, older models wasted a ton of attention on the very first token. This new gate stabilizes everything so the model can extrapolate to sequences way, way longer than what it was trained on.
Without any extra fine-tuning.
And connecting this to the bigger picture, it implies O1 memory usage during inference no matter how long the context is.
Okay, wait, say that again. Constant memory?
Constant memory usage. Whether you feed it a paragraph or an entire legal document, that is the holy grail for edge deployment, for running these massive models locally on your own devices.
Wow. Okay, so moving from that, from width efficiency to scaling depth, the best people runner-up was about reinforcement learning. They got to 1,000-layer networks.
Yeah, and for years, RL networks just couldn't get that deep. The old problem was stability. The reward signal in RL is often really sparse.
So you only get a thumbs up or thumbs down at the very end.
Right, and that sparse signal would just cause deep networks to collapse. So they overcame this by using contrastive self-supervision instead.
So it gets a dense, stable signal at every step by comparing its own internal states.
Exactly. Continuous, stable information. And it turns out this massive depth, it acts as a proxy for the agent's horizon of planning. Deeper a network, further it can plan.
Okay, so now we shift from these incredible architectural breakthroughs to a bit of a sobering reality check.
The reasoning conundrum.
The reasoning conundrum. The industry hypothesis was that reinforcement learning with verifiable rewards, RLVR, was the key to teaching models how to actually reason.
And RLVR, just to clarify for you, means using something like a formal proof or code execution to check if the model's output is correct, instead of just a human's opinion.
But a critical paper at NeurIPS delivered a major negative result. It showed RLVR doesn't really teach reasoning. It mainly just enhances sampling efficiency.
Which means it gets really, really good at aggressively pruning its search space to find answers that look like things it's seen in training.
So it's not learning to explore new logical paths. It's becoming a hyper-optimized pattern matcher.
The System 1 pattern matcher, yeah. It gets incredibly good within its base distribution, but it doesn't expand its capabilities beyond that.
But I have to ask, if it gets better at solving, say, 90% of the problems it sees, isn't that good enough for practical use?
And that's the tension, right?
Right.
For deployment, yeah, high accuracy on common problems is valuable. But for scientific discovery, you need true generalization. And this was compounded by research from Apple on what they call the jagged intelligence of these models.
The complexity cliff?
The complexity cliff. Performance doesn't degrade gracefully. It works, and then it just collapses. Past a certain complexity threshold, it falls apart.
I remember engineers saying that was the single most frustrating part of deployment.
It is, because you can't predict it. And here's the really wild part they found. The effort paradox. Once it passes that peak, the model's reasoning effort actually declines.
It gives up.
It literally gives up. It reverts back to simple heuristics instead of trying to deliberate. So this defines a very specific, bounded utility for these architectures.
Excellent in the middle, but they fall apart at high complexity.
Which is why the debate is still very much alive. We saw a counter-narrative from NVIDIA, their pro-RL work, suggesting that maybe just prolonging the RL training for much, much longer could eventually break that plateau. So the question is still open.
Okay, so we've established that architecture is getting more efficient, but reasoning is still bounded. The next logical problem is, how do you debug these things in the real world?
That's the pivot. The conversation is completely shifted from, look what my model can do, to how do we debug this system reliably? This is the birth of formal AI systems engineering.
And the agentic bridge framework was a key paper here, right? Arguing that the gap between benchmarks and real-world performance is a systems problem.
It is a systems problem. The framework proposes this three-layer architecture. The most important part is the optimization insights layer, which acts like a profiler to find those exact performance cliffs we were just talking about.
And it does this using trace-level telemetry. So you capture every single internal decision to debug the agent's thought process.
You're basically taking tools from complex distributed software and pointing them at the black box of an LLM.
And if we're building these systems, we need benchmarks that reflect that interaction.
Yeah.
Which brings us to CodeARC.
Right. CodeARC finally addresses how inadequate static coding benchmarks are. It forces the agent into inductive program synthesis. It has to interact with a hidden function, an oracle.
So the agent writes code, the oracle checks it.
And if it's wrong, the oracle gives back a counterexample, a specific input where the agent's code failed. The agent has to use that new data to debug itself and try again.
It's testing actual problem solving.
And the results were incredibly humbling. The state-of-the-art model, only a 52.7% success rate.
Wow.
It just proves you need this agentic loop. The data showed that for almost 30% of the problems, the initial description wasn't even enough to solve it. Agents that can't ask questions are just destined to fail.
So the fifth major theme is the maturation of AI for science. AI for science. It's officially graduated from being this niche application to a fundamental instrument for discovery. We're building scientific foundation models.
And standardization is the key shift. Take ML4CO Bench 101 for combinatorial optimization. By creating this unified benchmark, they revealed a kind of surprising truth.
Point was.
Many of the previous state-of-the-art results were leaning really heavily on old-school classical heuristics, not on the neural network itself. The benchmark forced some honesty into the field.
So the models were just running a fancy neural net on top of old tricks.
Pretty much. And we're also seeing models capable of what you could call real scientific imagination.
Like the Phoenix model.
Yeah, this is so exciting. It learns a joint space between a molecule's structure and what a cell looks like. This lets you do zero-shot biology.
So you can just ask it a question, like, find me a molecule that does this specific thing to a cell.
Exactly. You can query it with a desired outcome. It's a totally new capability for drug discovery that could let you bypass years of lab work.
Okay, so after all of these technical advances, we have to conclude this deep dive with the critical sociological warning that came out of the conference.
The artificial hive mind paper.
The artificial hive mind.
Yeah.
What I found shocking was their core finding. As models get fine-tuned with RLHF to be safe and helpful, their outputs converge dramatically.
Models from OpenAI, Google, Anthropic, they all start to produce identical arguments, the same phrasing, the same structure when you ask them about complex topics.
It creates a monoculture of thought.
It really does. If the vast majority of our information retrieval relies on systems that are all optimized to sound the same, that lack of variance could be a real threat to human creativity and critical thinking.
The warning from the study is so clear. We're optimizing for this very narrow definition of what helpful means. And if we all start getting the same synthesized arguments from our AI, our whole cultural debate just narrows.
Which is why the authors argue we need new metrics. Not just for accuracy, but metrics that explicitly reward semantic diversity. If all our models sound like one highly agreeable, polished voice, the cost to critical thinking could be immense.
So if you wanted the summary of AI in 2025, it's this. The magic of brute force scaling is fading. It's being replaced by the hard science of precision engineering, efficiency, and system-level accountability.
NeurIPS 2025 will be remembered as the year the field really looked under the hood, found the limits of just scaling up, and moved from that unchecked optimism to hard-nosed scientific engineering. The knowledge is now yours. Go forth and deploy responsibly. And if the foundation models that fuel our searches, our education, and our research are becoming hyper-optimized to produce the same arguments and phrasing, creating this artificial hive mind, what are the long-term societal costs of having our information environment lack that internal friction, that lack of divergent viewpoints? That's something for you to mull or explore on your own.